Welcome to Carnegie Mellon Online. For more multimedia from Carnegie Mellon University, visit www.cmu.edu/multimedia.
The idea of this panel came up, well, it just happened that I was reviewing a paper on technologies for carbon dioxide reduction that the Institute of Defense Analysis in their Science and Technology Policy Institute was preparing for the Office of Science and Technology Policy at the White House. And I kept seeing reference to CMU research. Granger's name, Lester's name, Ed's name, carbon sequestration, and I thought, this is very interesting. And then it came up that I was asked to participate on the committee for the homecoming, our 50th anniversary here, graduates from CMU, and the opportunity to present some panels sponsored by the class of 1957. And so I said, well, I think we should do one on climate control, global climate, because it's a hot topic and maybe we ought to think about nanotechnology. So as the class has decided that we would do those two things. So, and then simultaneously, I was called by some very committed scientists in Washington about this climate commitment program that Middlebury and Harvard were talking about, and this idea was that they would get their alums as they came into the reunions to think about what they could do to encourage their universities to make global climate and energy efficiency one of their priorities. And I thought, I don't have to do that with CMU, they're teaching us that. And then the CMU magazine came, and there was this great article on cool ideas by Mike Randall featuring Granger, and increasingly, we see more and more about this. So I called Lester and said, how about a panel? And he said, I think that's a great idea. And then Granger said yes, and by the way, if we want to talk about carbon sequestration, we certainly have to have Ed. So that was the basis. And then we have another participant, which I'll introduce his bio shortly. So with all that in mind, the SARs came sort of together and aligned. And then I was called by the university to tell them, and they asked me about the Steinbrenner Institute for Environmental Education Research, and I hadn't heard of this. And so Deb Lang talked to me about, we've produced, for the last 2 years, we put on an environmental seminar. And I said, well, great, why don't we sponsor this together? And so Dave and Deb have just been terrific, and their staff. And so as part of this, what I'd like you to do is pick up this little brochure that we put together that tells you as individuals what you can do to begin to think about climate control in your own house, in your neighborhood. I mean, we're really smart people, and we can influence our legislators, but they need to know that we're interested in this area. So what I'd suggest is you take this brochure, go home, think about what you can do in your communities to help change some ways people are doing business. Think about schools in your neighborhood, how they can begin to teach kids about climate control issues, and so forth. So pick this up on your way out. The Steinbrenner Institute helped put this together, and I appreciate your support in that. So let's proceed on with the panel then. So first I'd like to introduce Dr. Granger Morgan. And he has one thing I forgot to tell you that I wanted to mention. And that was, of course, that, I'm sorry, I'm messing up here. Of course, the fact that Al Gore received the Nobel Prize didn't hurt, and also that Ed Rubin was participating on one of the panels that has also received the Nobel Prize, which we'll talk a little bit more. But those of you who, Dave mentioned an article by Tom Friedman, but I happened to see one in the New York Times about a week or two ago. And Tom Friedman wrote about one council member in the city of New York who got together with an entrepreneur with the idea of changing the taxi fleet. And they encouraged the council in the city of New York to buy 500 taxis that were hybrids. These were Ford Escapes. And then, with great support from Major Bloomberg, they then proceeded to get a requirements of new legislation that says from now on, all new taxis will be green taxis. So they're going to have something like 15,000 taxis in New York City in time that will be hybrid taxis that will be gas efficient. And the taxi drivers love it because it saves them money on gas. And so his comment was, if New York goes green, the Big Apple goes green, people come to New York, 40 billion people pour into the city, ride in a green taxi, they'll go home and say, gee, why don't we have green taxis in our neighborhood? So this is one example of one person with an entrepreneur support saying, I can make a change in my neighborhood. So I just wanted to call your attention to the fact that you have a lot of power in your own neighborhoods, in your own school environments, and so forth to make some changes. So that's what this panel is all about. You'll get some suggestions. So first, I'd like to introduce Granger Morgan, who's professor and head of the Department of Engineering and Public Policy. He's the University and Lord Chair of Professor in Engineering. He has appointments in electrical engineering, Johns Hines School of Public Policy and Management, and he's the director of the NSF Climate Division Making Center at CMU and co-directors with Lester Lave, the Carnegie Mellon Electricity Industry Center. His research addresses problems in science and technology and public policy with an emphasis on characterizing and treating uncertainty in quantitative policy analysis. Dr. Granger serves as head of the Advisory Committee of EPA, which I certainly appreciate, and the chair of the EPRI Advisory Board. He is a graduate of Harvard College with a major in physics and an MS in Cornell and PhD from University of California at San Diego. He's been elected to the National Academy of Sciences, and the Steinbrenner newsletter has a special feature on that. So, and that's because he's been a consistent voice in the nation to curb CO2 emissions. So, Dr. Granger? Morgan, sorry.
Thanks very much. Actually, in addition to New York, Pradipto may be able to tell us about how New Delhi succeeded in cleaning up its air by switching all of its three-wheelers from cheap high-sulfur fuel to natural gas. It's made a dramatic change. I thought that I should start with a little bit of overview of the basic science, and then Ed and Lester will respectively talk about controlling emissions from power plants and controlling emissions from the transportation sector. Probably most of you know the basic ideas behind climate science, but I continue to be surprised by how when I brief folks, like, for example, a recent briefing I did for a FERC commissioner, some very fundamental things have been missed. And so, pardon me while I just quickly go through a bit of an overview. I mean, energy comes in from the sun, most of it, of course, in the form of light, some of it in the form of infrared. And about 30% of that is immediately reflected off the clouds and off the land and other things. The other 70% gets absorbed by the clouds, the atmosphere, and the ground. Now, if that just kept being absorbed, of course, we'd all heat up and fry. So we have to get it back out into space in order for the same amount of energy to be going back out as comes in. And that's where life gets a little complicated, because while the atmosphere is transparent to light, which of course is why our eyes evolved to be able to see with light, it's largely opaque for infrared because of absorption lines from both water vapor, but then also carbon dioxide. And that means then that the heat energy gets trapped and sort of goes round and round until the whole temperature of the planet warms up just enough so that the amount of infrared radiated off the top of the atmosphere is just equal to the amount of sunlight being absorbed by the system, and the planet reaches an equilibrium. This is a good thing for us, because if this weren't the case, it would be a rather unpleasant, cold planet, and this is a way, the so-called greenhouse effect is why Earth is a nice place to live. Now, of course, most of that energy comes in at the equators, and the poles would be much colder than they are, and the equator is rather hotter if it weren't for the fact that a lot of it then gets redistributed around the planet. About half of it gets moved polewards with the atmosphere, shown in the upper picture there, and then about the other half gets moved poleward through ocean currents. And I'll come back to ocean currents with an example in a few minutes. Now, we've been burning lots of coal and oil and natural gas, and when you burn those things, of course, the carbon in them combines with oxygen in the atmosphere and produces carbon dioxide. And the consequence has been that as the top curve there shows, since the Industrial Revolution began, carbon dioxide concentrations in the atmosphere have been going up and up. That's also true of a variety of other greenhouse gases, that is, gases that absorb carbon dioxide. And the consequence has been then that the planet has been warming. Now, all of this is a little abstract, so I have recently started trying to make the idea rather more concrete. Just west of us here is the Bruce Mansfield power plant. It's a little over 2,000 megawatts. Now, the coal for that plant, of course, actually comes in barges, but it's much more visual to think in terms of 100-ton hopper cars. A plant like that burns about 230 hopper cars of coal every day. And coal is, of course, not pure carbon. There's ash in it as well. If I only considered the carbon, that would be about 130 100-ton hopper cars a day. So every time you see a coal train with 130 cars, a Bruce Mansfield plant is taking that much mass, combining it with oxygen and sticking it in the atmosphere every day. And we've got, of course, hundreds of plants of this sort all around the world. So the mass involved is really pretty substantial. Now, the steady buildup of greenhouse gases, of course, has resulted in some warming, about 1.5 degrees Fahrenheit, or 1.25 degrees Fahrenheit over the last century. And the IPCC recently noted that you can see that sort of warming in all parts of the world. Now, the key point I wanted to make, and this is where at least some of you may have not quite figured it out from at least press coverage, because the press is often fairly confused about this issue, is that carbon dioxide isn't like conventional air pollutants. If I put sulfur dioxide or oxides of nitrogen into the atmosphere, they don't stay there very long, a few hours to a few days. So if I stabilize emissions of those gases, I stabilize concentrations in the atmosphere of those gases. That's not true of carbon dioxide. Carbon dioxide lives in the atmosphere, much of it, for 100 years or more. And so if I stabilize emissions, concentrations are just going to continue to build up and build up. If I want to stabilize concentrations, and of course it's the concentrations that matter in terms of absorbing the outgoing infrared, I have to reduce emissions by something of the order of 80% planet-wide. And that, of course, implies enormous changes in the operation of the planet's energy systems, which is why we're going to have two talks following this one on two important aspects of the energy system. Here's a useful analogy. Imagine a bathtub with a very big faucet and a very small drain. And this is basically what's happening in the Earth's atmosphere. Now, there's a key corollary. You often hear people argue, well, until China and India and Brazil do something, we shouldn't do anything. Well, sooner or later, China and India are going to have to get on board. But remember, I said it's concentration that matters. And so what I've plotted, actually Jay Apt has plotted on the right here, are two curves. The right-hand curve is emissions. And actually, it turns out China's emissions have been growing a little more rapidly than people thought. They're probably just about the same as America's emissions today. But because we've been at it for a whole lot longer than the Chinese, our contribution to concentration is much larger, and China's contribution won't catch up with ours until roughly the middle of the century, which is not to say, of course, that China and India and other developing countries don't need to do anything. It is to say, however, that we really need to go first and lead the way, show how these technologies can be made cost-effective. This graphic on the left is a lovely piece that the artist for the Pittsburgh Post-Gazette produced when a couple of us wrote an opinion piece on this subject. And you can see these blue molecules, which are U.S. Carbon dioxide molecules, and the red ones, which are to imply Chinese molecules. It's nice when an artist actually reads the opinion piece and produces a... So, isn't there enormous uncertainty about climate change? Yeah, there is, but there's no uncertainty about whether carbon dioxide and other greenhouse gases are warming the planet and changing the climate. And talk about uncertainty, to be frank, is basically the result of the intentional obfuscation of those with short-term economic interests. I mean, this has gotten better recently. I mean, there was a period a decade or so ago when there was sort of a united front across the industry on this. But in the electricity industry, for example, first those with lots of nuclear power broke ranks, and now a bunch of major coal companies have also begun to figure out that this is or coal-based utilities have begun to figure out this is a really serious problem, and we got to start working on it. The same is true in the oil industry. ExxonMobil is one of the last holdouts, and even they, of course, for years have had really good technical understanding of all of this, but have done their best to obfuscate. Now, there is uncertainty about how much greenhouse gas humans will add to the atmosphere over the next century, how much additional warming that's going to produce, and the details of many changes in climate and ecosystems and so on. So let me just give you 3 quick examples. It's still very unclear whether and how climate change may affect the frequency and the intensity and track of hurricanes. As a matter of fact, later this morning I'm meeting with a German postdoc I have who has been doing a very extensive review of the state of the science on this. And the state of the science is that we still can't tell. I mean, in the long run, there are plausible arguments for why climate change could have an effect, particularly on the intensity of hurricanes, but to date it's unclear. It's also unclear whether and how much climate change will affect the ocean conveyor belt, this large circulatory system, or also known as the Atlantic Meridional Overturning Circulation. And here are some results from an analysis that we did jointly with some folks at the Potsdam Institute for Climate Research. These were detailed interviews, expert elicitations with leading oceanographers all around the world. And so what's plotted there is if this is the amount of temperature rise by the end of the century, this is each expert's judgment of the probability that that circulatory pattern will shut down, or at least will have started to shut down or collapse, by which we meant a reduction of 90% or more in intensity. And you can see here's an area where the field is basically split. Now you might ask, so what difference does it make? And I simply remind you that both central Labrador and southern England are at exactly the same latitude. And while this is not the only phenomena that contributes to there being palm trees and subtropical gardens in southern England, it is clearly a major factor. And here's the third example. Fine particles high in the atmosphere reflect back into space, and so if we took away, and we put a lot of fine particles up there from the sulfur in power plant fuels and other things, if we reflected less of that sunlight back, then this would unmask some warming. So we did an analysis also with 24 leading aerosol physicists, and these things are box plots that show the amount of forcing. Down is cooling, and then the red bar up is the estimate of how much warming is being contributed by carbon dioxide. And you can see that if you look at the open dots in the cooling, you can see that there's probably quite a lot of warming being offset by the cooling effect of aerosols. Last thing I wanted to talk about before I turn it over to my colleagues is a few words about impacts. The largest amount of warming, of course, is going to occur at the poles. And there are models out there now that suggest that the Arctic Ocean may be completely free of sea ice by the end of this century. This is a result of a run of a Canadian model there on the bottom. And here are some NASA and NOAA actual illustrations of the extent of sea ice cover by the over time. Notice that there's still sea ice right up against northern Greenland, and that's important because if that goes away, then that will result in even further warming of Greenland. Now, while the Arctic is vulnerable, so too are small island states and coastal estuaries because of sea level rise. Mangrove swamps, and your reaction might be, who cares about mangroves? Well, it turns out that this is the breeding ground for many, many aquatic species. Alpine meadows, why? Because as climate warms, they'll be driven right off the top of mountains. and coral reefs. Both warming and also sea level rise are already having significant effects on coral reefs. Now, as you can maybe tell, I grew up in New England, and the other effect will be impacts on many ecosystems that we hold dear. I grew up, for example, in central New Hampshire, and the notion of New Hampshire, my great-great-great-grandchildren may find New Hampshire with yellow pine and oak just fine, but the notion that there won't be sugar maple, birch, and white pine, I find really quite disturbing. Now, water expands as it heats, not very much, but a little bit, and the oceans are big. And so there has been regular increase in global sea level. Those estimates are the ones just published by the fourth assessment. It says Working Group 1. Yeah, that's right. Working Group 1 of IPCC fourth assessment. But what these guys did not think about, or at least didn't write about, was the fact that there are some new studies suggesting that Greenland may be losing its ice cap a lot faster than anybody had thought. Now, sea ice, if you melt it, doesn't change sea level. It's like, you know, if you have an ice cube in a drink and it melts, the drink level doesn't change. But there is growing evidence that we're seeing rapid melt on Greenland, and furthermore evidence that some of that water, rather than just running off the top, goes down underneath, lubricates the underside of the ice, and accelerates its loss. And so I'm going to end with a lovely slide that Dan Schrag at Harvard produced. Pick your favorite place along the Gulf Coast or in South Florida, and now I'm going to melt half of Greenland. That's about 3.5 meters of sea level. And I'll cycle back and forth. Incidentally, in the introduction, it was explained that I chair EPA's Science Advisory Board, and a few years ago in Region 6 down here in this part, we got a briefing on all the wonderful things the agency was doing to restore coastal wetlands. You know, all of these things along here, and I asked them, you know, spending millions of their dollars and other people's dollars, and I asked them, you know, how much have you thought about the implications of global warming and sea level rise? And the answer was not at all. Now, if you've not seen it and you're interested in learning more about impacts on the U.S., though it's now a few years old, the U.S. National Assessment, published just at the very end of the Clinton administration, is still really quite good. You can find it online. Just do a search for U.S. National Assessment and Google will produce it for you. It's also been published by Cambridge University Press. There was a big flap when the Bush administration came in trying to suppress this document, but it's quite a nice piece, and it goes through and talks about a wide variety of impacts. It also talks about impacts in regions all around the country. With that, I'm going to call things to a close, and Ed, are you going to go next to talk about the electricity sector, which is the single largest sector producing carbon dioxide, and then Lester will talk a bit about automobiles. And as Lester may explain, the two are actually linked, because one of the promising technologies for dealing with the emissions from automobiles is plug electric hybrids.
Let me just give a little introduction. Ed, you're going to go next then. Dr. Rubin is professor in the Department of Engineering and Public Policy and in the Department of Mechanical Engineer. He's chair of the alumna professor of Environmental Engineering and Science and founding director of the Center for Energy and Environmental Studies and the Environmental Institute. His BS is in Mechanical Engineering from the City College of New York and NMFs and PhD from Stanford. His teaching and research in the area of energy utilization, environmental control, with particular emphasis on co-utilization and carbon sequestration. He has served on the advisory board for EPA, Department of Energy, National Academy of Sciences and Engineering, and was the lead author in the Intergovernmental Panel on Climate Change on Carbon Capture and Storage, which, as you know, has just been named with Al Gore as a participant in the Nobel Prize. So, I introduce Dr. Rubin.
Give me a second. We, even though we're computer U, we have not yet successfully resolved the PC-Mac dichotomy. Let me see if we can get this going on.
Yeah, you can blame this on me.
I think we're showing our age where neither of us are, let's see, what are we doing? Let's see if that works. This is always the moment of truth. Okay, now if I do it one more time, I should, okay, now I get to see it as well. Very good. Okay. So the division of labor that Granger and Lester and I agreed to is Granger was going to give the overview of climate. Lester and I are going to talk about what I expect most of you really came here to talk about, how to reduce greenhouse gas emissions. I will focus largely on the utility sector, but I want to get to it by first talking about this issue and more generally. First, Granger went through it quickly, just to recognize that when we talk about greenhouse gases and the climate change problem, while carbon dioxide, CO2, is the main focus of attention, properly so because it's what we emit most of and it has a long life. There are other gases as well. Methane, N2O is nitrous oxide, and a variety of other organic and inorganic chemicals that have this same effect. The properties that they have in common are that they trap incoming sunlight, and they all have very long residence times in the atmosphere. So once you put them in the air, they don't go away very quickly. Just because of the time constraints, I want to focus on the CO2 problem. Part of what the science community has been trying to do over the last couple of decades is try to understand how you could put these on a common footing, and there's a concept called the global warming potential, which has evolved, GWP. And on that kind of weighted basis, on kind of a 100-year time frame, the CO2 problem, both nationally and internationally, has something on the order of an 85% effect of the total issue. So it's clearly the 800-pound gorilla in the room, and that's the one I want to focus on today. Let's talk about where CO2 in the U.S. comes from, and it comes from the things we do and the things we like to have. So the end users are communities are lumped here, basically buildings, residential and commercial buildings, industrial processes, and transportation. And the different colors show different fuels. So here's transportation with about a third of the U.S. CO2 emissions. It's all blue, meaning it all comes from petroleum. It's basically a one energy source issue. It's burning gasoline. When we look at buildings and industrial processes, it's more varied. Actually, in buildings, the lightest bar at the top comes from electricity. We don't generate electricity in our own homes and buildings. We'll talk about that in a second. The other bars represent the direct use of fuels. So one of the things that one has to understand is not only what can be done in each of these sectors, but where electricity which is used in all of these sectors, comes from, and that's what this picture is showing. A lot of people are still surprised to learn that we still use coal in this country. More than half of our electricity nationally comes from coal. Here in Pennsylvania, it's actually a more sizable fraction. And that coal alone contributes, again, about a third of the total CO2 emissions in the country, and the rest of the CO2 emissions, the yellow bar, comes from burning natural gas, which has increased a lot in the last last decade in particular. So a short take-home message is that electric power plants, electric generation, and vehicles together account for about 75% or 3/4 of the total CO2 problem. Okay? Coal from power, oil from vehicles, those are the two issues that we really have to get at. Here are some projections that the Department of Energy made earlier this year. The DOE puts out, the Energy Information Administration annually puts out an annual energy outlook, which currently looks out to the year 2030. And they publish what they call a reference case scenario, which has all sorts of assumptions about the future trends in prices, future efficiency improvements in technology. One thing they are not allowed to do by law, though, is to make any assumptions about how policy will change in the future. So all of their analyses are based on no change in current policy. This reference case scenario gets a lot of visibility, a lot of attention. A lot of people believe it to be a forecast. Raise your hand if you think there'll be no change in any policy in the next 25 years. I don't either. So we know that this is not going to happen. But it's still an indication of what might happen absent any policy driver. And what we see are increases in all sectors of the U.S. economy, with the total CO2 emissions increasing by about a third from now to 2030, over the next 25 years. The biggest part of that increase, the fastest growing sector, is actually the electric power sector. Electricity is something we're using more and more of. All the computers and electronic gizmos that are new to us just in the last decade or two are actually one of the fastest growing sources of power generation. That ain't going to stop. And so with the electric sector alone, we're looking at about a 40% increase in CO2 emissions. And most of that is coming in these scenarios from projected significant increases in the use of coal. Why? Because natural gas, which we've been building a lot of in the last decade, has suddenly got a lot more expensive. Coal is still relatively inexpensive. And when you allow these fuels to compete in the kind of models that produce this scenario, these are the kinds of results we get. So what can you do to reduce CO2 emissions? Not in a small way. The key point in Granger's talk was that if we're trying to stabilize the concentrations of these gases in the atmosphere, which is the international goal that has been agreed to, it's not going to take a 5 or 10 or 15% reduction in emissions. It's going to take a 70, 80, 90% reduction in emissions over the next century kind of time scale. So we're talking about big moves, not small moves, and that is one of the key problems here. So how do we do that? Let me just go through a couple of slides that we will probably want to talk a little bit more about in the discussion phase. One thing we could do is to develop and use more efficient technologies simply to reduce the demand for energy without sacrificing the amenities. I would assert there is no technology that we use today, anything from the light bulbs in this room to the cars you drive to the refrigerators and air conditioners and space heaters you have at home, that cannot be engineered to use less energy and provide the same service. In fact, in many cases, we've made remarkable advances in doing just that, but often it requires spending more up front to save energy during the life of the issue, of the technology. There's not always incentives, because often the people who buy stuff aren't the people who gain the benefits of using it. And often in the marketplace, there is often a disincentive to have products that are more expensive than your competitors. So regulations have played a role in prompting that, and there's just a lot more that can be done basically across the board in all of the areas shown here. There are other things that we can do to reduce the demand for energy services and energy-intensive products. Some of these have nothing to do with technology. A lot of them have to do with lifestyle changes, driving smaller cars instead of trucks, carpooling instead of one person per vehicle. Those are the kinds of things that can also make a difference. Other broader things, changes in community planning and development. We've got urban sprawl that is contributing in large part. So how we live, whether we build out or up, makes a big difference. Transportation systems and infrastructure, the kinds of products we manufacture, and various things related to agricultural practice. All of these are things that can involve us individually. And then finally, in terms of other things we can do, and we've already had some discussion of this earlier today, we can start to try to use technologies that with energy sources that have lower or no greenhouse gas emissions. that is trying to move away from coal and oil toward the use of things like natural gas, which has about, for power generation, has roughly half the CO2 per kilowatt hour of electricity compared to coal. We've already started the discussion of nuclear power. A lot of people like the idea of renewables, wind, biomass, geothermal, solar, and hydro. All of these are on the table. All of these will be players in any serious strategy to deal with the climate issue. But what is also clear from a lot of thought and a lot of analysis over the last decade is that there's no silver bullet, there's no single solution. Every one of these options have their own sets of issues and limitations that go with it. The other thing to keep in mind is just the scale of deployment that you would need to have significant reductions. In the US alone, we'd be talking about either retrofitting or replacing literally hundreds of millions of buildings and end-use devices and widgets, tens of millions of new cars per year, and literally hundreds of power plants around the country. So it ain't gonna happen quickly. It's gonna require the massive deployment of technology on a massive scale, and it's not gonna happen overnight. There's one additional approach to reducing CO2 emissions that was already mentioned earlier in the Steinbrenner session. A number of you weren't here at that. And I wanted to spend a little more time on this because it's probably the one that might be least familiar to you because it's been a relatively new player in the mix of things that have been talked about and analyzed for addressing greenhouse gas emissions. And that's the notion of technologies to capture and sequester the CO2 produced at power plants and other large sources. There's a nomenclature issue here. The term carbon sequestration up until just the last 4, 5, 6 years has largely been used in the context of what is now being called terrestrial sequestration. That is the uptake of CO2 from the air by trees and vegetation. And that actually has a legal, the word sequestration, carbon sequestration, actually has legal connotations in terms of treaties that are geared toward that. Today, that term also now includes technological methods to capture CO2 from smokestacks and large sources and put it somewhere, sequester it so that it stays out of the atmosphere. There are a number of acronyms that have been developed. CCS is the one that seems to have emerged as the main way of talking about this, and it's carbon capture and storage, or carbon capture and sequestration, depending on your choice. Okay. Let me tell you a little bit about this and just kind of get you up to speed on this if you haven't seen it before. The notion basically is that here are various products. This could be a power plant or a chemical plant of some sort, something large that uses carbonaceous fuels. We talked about fossil fuels. It could also be biomass. And the notion is that there's CO2 produced in the processing of this on the way of getting useful products. What we need to be able to do is capture that CO2, separate it from the other gases that it typically is mixed with, compress it till it becomes a liquid. That makes it easy to transport it through a pipeline to where you would inject it typically into deep into the ground, into a geologic formation to keep it out of the atmosphere. I'll talk a little bit about that in more detail. There are potentially other ways of sequestering CO2. You actually could put it deep in the ocean. There are issues associated with that. There are a number of other things that are kind of in lower, less light font down there that have been looked at, which I won't talk about. Geologic formations are the key issue that are being looked at today. Why the interest in CCS? It's fundamentally comes from the realization that in a world and in a country that is 85% reliant on fossil fuels for our energy, that's not going to change quickly or rapidly. So the notion is that fossil fuels, especially coal, which is the most carbonaceous of the fossil fuels that we use, is going to continue to be used for many decades. There's just no way of not doing that easily. And all of the alternatives, you can pick your favorite, whether it's nuclear or renewables or whatever you like. Those are simply not likely to achieve the large reductions in CO2 in the timeframes that are of interest to the policy community. So the reality is that we're going to be putting more CO2 into the air if we keep using these. And CCS then, the capture and storage, potentially would allow coal and other fossil fuels to continue to be used with little or no CO2 emissions. I like to think of it as a bridging strategy to a more sustainable future, because it's going to take time to develop all the other things that we think could do that better job. And as Granger just mentioned, it's also very interesting. It's that it offers, actually for the first time, a potential link between what we do to generate electricity and what we do to move ourselves around. Because we can start to imagine an electrically driven transportation system where the electricity is carbon-free. We could produce hydrogen from fossil fuels, also in a way that's carbon-free, but sequestration is the key to making the carbon-free part of that work. So it's been getting a lot of attention. The other reason it's of interest is that when folks are running these big energy models to look at 100-year futures from around the world to do that, including this capture and storage option in the portfolio of all the other things I mentioned, actually saves a significant amount of money. It's kind of makes sense. Any portfolio, the richer a portfolio, typically the more effective it is, and that's the case with this as well. There's a lot of detail on this technology in a report that was produced just about 2 years ago by the Intergovernmental Panel on Climate Change, and I'd recommend you to their website. I would not recommend you read the full technical report unless you really want to dive into this. Start with a 10-page summary for policymakers. It's a very readable document and might be a way to get started. The leading candidates for this basically are large sources. Most of the CO2 that we currently emit and will be emitting for the next decades will be at fossil fuel power plants, so that's the place to go. There are different types of plants. There are some large industrial sources. Pipelines and geologic sequestration are the ways that keep CO2 out of the air. There's a lot of activity worldwide on this, which is the other part of the message. There are CO2 capture projects around the world. This is not a new technology that needs to be invented. The technology for separating and capturing CO2 is commercial. It's been in use for many decades. Most of the use has been not in the electric power industry, but in petroleum and petrochemical plants, such as the one I'm showing you here on the left. It's also used in a coal gasification plant in North Dakota. So it's commercial technology. We know how to do it. We know what it costs. The same technology has actually been used on power plants. Here are two examples of plants, one in Oklahoma and the other one in Maryland. Not the entire plant, but only a small portion of it is being treated for CO2 capture, basically because CO2 is an industrial commodity. People pay good money for it. Both of these plants capture the CO2 and sell it across the fence, typically to a food processing plant that uses it, and then it goes out into the atmosphere. So it's been used in power plant applications, but on a scale that's about an order of magnitude, a factor of 10 smaller than a big commercial plant. CO2 pipelines are also nothing new. I don't know how many of you know about it. I didn't realize it until I started getting into this business years ago, but we've got thousands of kilometers of CO2 pipelines, mostly in the western part of this country. A lot of it takes CO2 from natural sources. Just as you drill for oil, you could drill for CO2. There's a lot of natural CO2 in the ground. It's pretty cheap to get out. And so what they do is they take it out of places like this and they ship it to West Texas and use it for what's called enhanced oil recovery. It has very lubricating properties and helps get more oil out of the ground. And that's the major use of CO2. We use about 40 million tons of CO2 in the country today for that purpose. And there are pipelines all over that have been operating for many decades. There's also a lot of activity internationally on the sequestration, the geologic sequestration of CO2. This map shows a number of places around the world. There are 3 big projects, big meaning 1 million tons of CO2 or more a year. Here's a picture of 2 of them. These are both at plants that develop natural gas. Natural gas, when you dig it out of the ground, actually has a lot of CO2 mixed in with it. And so that CO2 is typically separated out to get at the gas we want and typically vented to the atmosphere. Well, about 15 years ago, a little less than that, Norway put a tax on CO2 emissions for offshore operations, and that was enough to convince Statoil, who are developing gas in the North Sea, to take the CO2 and instead of putting it in the atmosphere, put it back under the ocean floor into what's called this deep saline formation. That's been going on for over 12, almost 13 years now. Very carefully watched and carefully monitored facility. This lower picture here is in Algeria. This is a BP plant that came online about 2 years ago. BP is doing this on their own nickel just to get some experience with it because they think they can make some money. Here's another recent project. I mentioned that there's a plant in North Dakota that's actually using coal to produce synthetic natural gas. And in that process, again, to produce natural gas, you normally have to separate the CO2 out and typically vent it to the atmosphere. Well, for the last 2 years now, about 1 million tons of that CO2 has been shipped to southern Saskatchewan. There's a 200-mile pipeline that was built. These are not big, there's about 18-inch pipelines. They're not one of these huge things. It's shipped as a liquid, basically. And it's used for enhanced oil recovery, but in this case, it's also being used for and monitored for permanent sequestration of that CO2 at the end of the life. When one looks around the world, again, one of the reasons that this has become a hot topic is that as best we could tell today, there's a lot of acceptable geologic storage capability around the world in places where the CO2 is. So you generally don't have to go very far from these big sources to find geologic sites that would be acceptable and would keep CO2 out of the atmosphere. There's a lot of interest and some concern and discussion about how safe is it? If you put it down there, is it going to stay there? What's it going to do to me? We can talk about that in the discussion. Bottom line, though, is that the longer it stays in the ground, the safer it is and the longer it's going to stay there because over time, the CO2 begins to dissolve in the brackish, briny waters, and over longer periods of time, it actually turns into rock, into carbonate rocks. So it has very different attributes than other kinds of waste that we sometimes talk about putting underground. Cost is a big issue. These are not inexpensive technologies. There are lots of ways of talking about cost. I'm choosing one here that's relatively simple because it's a number you can remember and kind of compare to some of the policy numbers. So if I put today's technology on a power plant that burns coal, and if I have to pay some money to put it down underground as opposed to somebody paying me to get it out with enhanced oil recovery, something on the order of $50 per ton of CO2 avoided is what it's going to cost me. There's actually another way of generating electricity that has been gaining a lot of attention because it affords a much easier way of capturing the CO2, and that involves not burning coal but gasifying it. You might have heard the acronym IGCC, Integrated Gasification Combined Cycle. Without CO2, it's a somewhat more expensive technology, but with CO2 capture, in most cases, it's actually cheaper than what we're doing today. And that comes in at something on the order of $30 per ton of CO2 avoided. The kinds of legislative proposals that are being talked about here and which are already in force in Europe have carbon prices more on the order of $10 to $15 a ton of CO2. So there's no economic incentive for this thing to happen right now under the legislative proposals that are around. It's also important to understand, we've done a lot of work at Carnegie Mellon here and looking at how things change over time. Technology innovation is a very powerful force, but you need a market for technologies to do that. We can see costs coming down significantly in the future if this technology came on. So here's some results of some modeling studies that show how carbon capture and other options come into play in trying to meet emission goals. There are a number of barriers to deployment, first of which there's no reason to do it right now. It has high cost. We don't have regulations yet for details of putting it into the ground, legal issues, and lack of experience. A lot of these are the kinds of things we're working on in research here at Carnegie Mellon. So this is my take on Granger's uncertainty slide. Future is uncertain. A lot of it will have to do with how climate policy develops. Okay, thanks. Lester?
Thank you very much, Ed. That answers
Okay.
a lot of questions.
Okay.
While Ed is working with his slides, I'll introduce Lester. We do have somewhat of a time constraint because President Cohen's speech is at 10. Lester Lave is University Professor and Higgins Professor of Economics at CMU. He's appointments in the Business School and the Engineering School and the Public Policy.
And that's fine.
All right, but
Thank
one point I do want to make, since I mentioned that Granger was elected to the National Academy of Science, is that he's also been elected to the Institute of Medicine of the National Academy of Science. So we have three very astute people here. And one word about that.
One of the issues, you've just heard that technically we can do this stuff. The big fear about this is that it's going to be so expensive that it will ruin our future. And that's really what I want to talk about more than other things. If you're not careful about this stuff, then it can be ruinously expensive. If you are careful about it, our best calculation is that the amount of money it will cost the United States will be about comparable to what it is we spent on abating pollutants in the 1970s and 1980s in the United States, air and water pollutants. But it is of that order of magnitude. Our economy survived that. And so if we do this in a clever way, our economy will certainly survive this. So this is just a picture particularly appropriate for Computer U of what it is my characterization is of current energy policy, right? It says, technical support says, first try rowing faster. That's what energy policy has been in the United States. So the first thing I need to be straight on is that for the last 150 years, the whole industrial era has been powered by cheap energy, particularly in the United States. That era is gone, right? That is, if you think that gasoline is going to be $1.50 a gallon sometime in the next few years, you're smoking something, right? That era is over. And we have to plan for a future where energy is going to be a lot more expensive than right now, but that's not a particular problem for our economy. The reason why energy is more expensive is because of environmental concerns and because of it's just more expensive to get energy out of the ground than it was in the past. Our reaction, our whole economy has been built on cheap energy. And that doesn't mean that we can't turn this around. It just means that we've got to change things the way. Did you know that there are more than one car per licensed driver in the United States? Right, almost 1.2 cars per licensed driver. I have this picture of getting two convertibles, right? I rig them up so I've got my right foot in one, my left foot in the other, and have a steering wheel up here and go down the highway. That's ridiculous, right? Well, if you're driving a Hummer, right, or if you're driving a Ford Expedition, something of that sort, that's basically what you're doing, right? That is, you're driving 5,000, 6,000 pounds of car down there, and it's the equivalent of having these two convertibles. So that doesn't even take account of that. The fact is that energy is really cheap, and we have a lot of vehicles in the United States. We had fuel economy legislation in 1975 after the OPEC embargo. It said that we had to go to 27.5 miles per gallon for automobiles. That's the top line, the line that's shown up as black here. You can see that we achieved that in the 1980s, and it's basically been there for a long time. EPA's estimate is that if we had taken all of the improvements in engines and transmissions over that period of time, we'd be at about 33 miles per gallon. But we didn't. We took all of the improvements in terms of acceleration. Our 0 to 60 mile per hour time is 50% less than it was in 1974. and we took it in terms of larger, heavier cars. And so we've got cars that Americans like to drive more than they did before, but not in terms of fuel economy. In 1974, about 10% of the new vehicles sold were light trucks. Now, more than 50% of the new vehicles sold are light trucks. Sports utility vehicles, pickup trucks, minivans, and so on. That's the bottom line in the graph here. Again, there was a fuel economy standard for those of about 20.7 miles per gallon, and those have been flat for this period. The yellow line in between, a little harder to see, is the fuel economy of the average new vehicle sold, which has been going down because we have bought more and more of these light trucks. So why is this important? Well, they talked about CO2. I want to turn away from CO2 for a second, right? We're actually spending at the moment about $360 billion a year for our oil. And I like this quote for Lenin. I come from a business school, right? You know we're all left-wing people. So one of the things we do in our business school is, at least I read Lenin, right? We have a quote that says, the capitalists are so hungry for profits that they will sell us the rope to hang them with. And I've added on a Lester Lave quote, which is, and they will send us the money to buy the rope. So what can we do about this stuff? I am chairman of a new panel for the National Academy of Sciences worrying about energy efficiency, fuel economy. And one of the things we know how to do is we know how to improve fuel economy by hybrid electric cars. That is not what we are doing. The hybrid electric cars you buy now, with the exception of the Prius, one exception, are built for power, not for fuel economy. That Ford Escape Hybrid is a wonderful car to drive. You step on the accelerator and that will go. You take a look at the fuel economy of that, it's 1 mile per gallon greater than the Escape that doesn't have the hybrid. Okay, those are all geared for power. Dumb old Toyota. I mean, Toyota introduced the Prius, 50 miles per gallon, a really fuel efficient car, right? And Detroit then learned how to make these hybrids that gave you power, and they sold like mad in the United States. And so Toyota since then has not made the same mistake again. The Toyota, Lexus, and so on are now all cars that give you lots of acceleration. That's what Americans seem to want to buy. But we can get the greater fuel economy with cars that you would like to drive. Our architects here told me, and I didn't believe, that we could improve the energy efficiency of a new high-rise building by about 80%. I've since talked about all sorts of people around the world, and they say, yes, yes, that is certainly true, right? And if you go to the Intelligent Workplace here, you can see that that's a building you'd rather work in rather than the one that you currently work in. We know how to improve lighting and air conditioning by 50% plus, certainly with respect to lighting. We can do all of those things with no perceptible change in lifestyle, right? That is that you wouldn't notice the difference. Why don't we do that now? The answer is energy is just too cheap, right? I mean, you may think that $3 a gallon at the pump is a lot. Go to Europe, you're talking about $7 a gallon. Those economies haven't collapsed under that. Energy is simply too cheap in the United States. Here's one solution for how it is we could get rid of all gasoline in the United States, right? And these are using technologies that we currently know about. They're not as economically attractive as they might be, but we know about these technologies. We know that we can replace gasoline with ethanol. The ethanol that people are talking about now is a blend of gasoline and ethanol. If you go to Sunoco, you can buy a blend that's 10% ethanol, 90% gasoline. If you go down to Brazil, you will find that you can pull in a pump and you can buy either a gasohol, which is 27% ethanol, rest gasoline, or straight ethanol. And you can put any one of those in your flex-fueled vehicle. That flex-fueled vehicle is made by GM, Ford, or Chrysler. Right? And you don't have to tell the vehicle anything, just put it in, the vehicle knows everything about it. Right? And so We could do that in the United States, but we currently use 150 billion gallons of gasoline a year. We can't make enough ethanol to replace that. That would require about 200 billion gallons of ethanol to replace that. So that's too much. But if we had all these cars be hybrids, not with my 50%, well, I guess my 50% improvement almost, then that would require 150 billion gallons of ethanol. That's still more than we can do, but there's this concept called a plug-in hybrid. If you put a battery on a car that will take the car 30 miles, that will save 2/3 of the fuel that you use. Right? That is that almost all the trips we make in the United States are about 10 miles, and we drive our cars about 30 miles a day. And so if you had this 30-mile battery, we could save 2/3 of the fuel, which means if we had these plug-in hybrids that we would need only 50 billion gallons of ethanol a year. We can easily do that. Not with corn. Corn is a big mistake. But we can do that with cellulosic ethanol, ethanol made from wood chips, from grasses, and so on. We can do that relatively inexpensively. But if you're going to do it, then what we need to do is to have some floor on the price of oil. And $80 a barrel is a floor that would certainly work. We're above that now. No big deal about that. Here's my last slide. These are data from our Department of Energy. I didn't make them up. There's a comparison, just look at the top two, between Denmark and the United States. The last column over there is BTU per capita, which is basically income per capita. If you look at Denmark versus the US, this is 2002. The Danes were slightly richer than we were. Don't believe the numbers particularly. I don't know what the difference looks like. Basically, we're the same. If we now go to the first column, it tells you energy use per dollar of GDP. We're at 45%, or sorry, the Danes are at 45% of where we are. We use twice as much, more than twice as much energy per dollar of GDP as the Danes use. The middle column is energy use per population. Again, the Danes use less than half of what we use. Anybody ever been to Copenhagen? Anybody? They walk barefoot on dirt floors, right? Danes live pretty well. Right? I mean, if you handcuffed me and you made me go to Copenhagen to live, I wouldn't cry a lot. Right? I mean, that's a really pleasant lifestyle. Less than half the energy that we use. Right? And that is not a mild climate, particularly. Right? So the point of this slide is that there's a lot we could do in the United States. We would have to change our lifestyles. The Danes have fewer cars per capita. The cars they have drive fewer miles per year. They tend to live more in high-rise buildings. They tend to take more public transportation and so on. Those are certainly all things that we can do. The point of this is that, just to sum up, the first one is that if we're going to do these things we're talking about, we need to pay a lot of attention to what the costs are. We will not be penalizing the economy if we can do these in an economic way. And there are several ways in which we can do them that are almost free at the moment in terms of increasing efficiency. And then more generally, if we want to get our 80% reductions, which we can do, then it's going to take some lifestyle changes as well. And I'll then expose myself to the world and say, do you really need to have one person driving a Hummer to work? Right? I mean, if you look at the highway, about 1 car in 10 will have more than 1 person in it. So do you need to have this huge vehicle, 6,000 pounds or whatever it is, with 1 person inside? Wouldn't it be just as well if you had a Prius-sized car? I've been in the back seat as well as the front seat of a Prius, right? Suppose that we had 1 person per car in that. Would we be breaking the hearts of Americans? And so I think the kinds of lifestyle changes that we're talking about are also perfectly good. At this point, let's stop. I think that we're going to try and have some time for questions.
We have one additional speaker that is Pradiko Ghosh, who's Secretary, Ministry of Environment and Forest for the Governor of India. And he has just recently been one of the honorees of Carnegie Mellon Alumni Association. So just come up and say a few words, and then we're going to have
So
a
I don't get in trouble with our president, just so folks know, we
Yeah,
have about
okay,
10
yeah.
minutes to go.
10 minutes.
So what I'll do is I'll skip my presentation and just make some, observations extempore. Okay. Let me give some. Granger mentioned about the New Delhi experiment with, with conversion of the vehicles fleet to compressed natural gas. This was motivated not so much by climate change concerns as by local air quality concerns. And what this essentially required was conversion of the entire bus fleet, almost the entire taxi fleet, and then of course in developing countries you have these three-wheeler taxis, they're called by various names in different countries, and the conversion of that entire fleet to CNG. Now, of course, what has happened is that as a consequence, but not entirely as a consequence of this changeover, there has been a tremendous improvement in air quality in the city of Delhi. And it's very obvious. If you were there 5 years ago and if you're there now, there's a huge difference. But this is not the only thing that happened. There were several other things that happened, and the jury is still out on precisely what the conversion of how much of this change is actually due to this CNG conversion. Now, this was a massive effort because it involved retrofitting existing vehicles, it involved phasing out of old vehicles, it involved creating entire new infrastructures for supply of the natural gas. And there was actually, because this was a very hard regulation which was enforced very strictly by the courts, this resulted in significant, disruption for a period of several months in the transportation system. But the results of that, of course, have been, at least to a significant extent, that this has had the major impact on air quality. It may have had a significant impact also on the GHG emissions, but once again, we don't know for sure because we have to really do the empirical work to determine how much of the savings in carbon emissions from combustion of CNG is offset by actual leakages of CNG. Methane, has a very high global warming potential. Now, of course, we had the first speaker who spoke extensively about buildings. Now, let me tell you about the Indian program with respect to buildings. Large buildings in India, they are subject to two kinds of regulation in respect of the environment and energy efficiency. We have the environmental impact assessment requirement for buildings which have an activity area of 20,000 square meters or more. And we have the buildings energy code, and that goes down to a smaller activity area, probably about 5,000 square meters or so. The environmental impact assessment requires that each building which qualifies for regulation to submit an environment management plan. And the environment management plan, of course, it relates to dimensions of energy use, it relates to water conservation, it relates to building waste management, it relates to recycling of used water. There are many different dimensions that it relates to landscaping. And there is a point system and a star rating system. Now, the developer is free to choose combinations of various measures under each of these categories, and each has a certain weightage in terms of the rating scale. There are some which are mandatory, and of course he's required to do the mandatory measures, and he doesn't earn any points for that. But then there's a qualifying level. If it's below those qualifying marks, then he doesn't get environment clearance. Back to the drawing board. But then if he does better than that, then depending on the actual qualifying scores achieved, there is a star rating, gold, silver, bronze, which are given for buildings which exceed this normative requirement. There's also the building code, energy code, which again provides for a menu of measures in respect of lighting, in respect of space cooling, in respect of insulation, and so on. Now, at this point, the building energy efficiency code is voluntary. and the idea is to get the building sector accustomed to these measures, to create a market for for these technologies. But then, of course, the idea is that in due course this will be made mandatory. Let me at this point give some examples. The institute with which I'm associated, TERI, all its properties are green buildings, and there is a campus which is close to the city of New Delhi. If you visit the city of New Delhi, you can arrange a visit, which is energy neutral. All its energy requirements are met from solar and biomass. There is complete water recycling. There is a very innovative, system of space conditioning by which, by which air is actually circulated below the ground at a depth of more than 2 meters, and that's a point at which there is basically a stable temperature throughout the year. So this means that in the course of 12 months of the year, there are only about 2 months where supplemental cooling is required. But all the space conditioning requirements are met by this system. Now, I think that we've run out of time, so I'll stop here. Thank you for the opportunity of making this presentation.